Hello everyone, my name is Tia Hussain. Today I will be presenting shell balance applications in transport phenomena focusing on heat transfer and mass transfer problems. So here I have taken 4 questions related to this topic and we will be discussing them thoroughly. So the first question comprises of this concept, that is temperature profile in a solid cylinder with uniform heat generation. So when the heat is generated uniformly inside a solid cylinder, temperature varies with radius. Since the ends are insulated, the heat flows only in the radial direction. And using the energy equation in a cylindrical coordinates and applying steady state conditions, the temperature distribution can be derived. And here we have to derive the temperature profile at steady state if that solid have a constant thermal conductivity. So this is our question. Then the given, let us move to the solution. The things given here are uniform heat generation, which is equals to Q, steady state, radial conductivity only, and constant thermal conductivity. And this is the boundary condition that we have here. After that, for solving this question, the general energy equation that we are going to use here is for the cylindrical coordinates, and we need to include the term of heat generation. So the final rate of change of temperature with respective time is given as this. Now we have to apply the assumptions, which are steady state, matlab the rate of change of temperature is equals to 0, and for only the radial conduction, the general energy equation will reduce to this, as there is no variation in theta and z direction. Then after rearranging this equation, multiplying the whole equation by r, we are getting this equation. And we need to integrate this equation twice in order to get the final temperature profile. So after integrating, after first integration we will be getting C1 constant, then second integration we will be getting the equation for temperature with C1 and C2 constant. Then for finding this constants we need to apply the boundary conditions, so we will be getting C1 ka value and C2 ka value. After putting the C1 and C2 in the temperature equation, we will be getting the final temperature profile as this. So the conclusion is, thus the temperature profile in solid cylinder is parabolic in nature, and the maximum temperature occurs at the center, R is equals to 0. The minimum temperature is at the surface, R is equals to capital R. So this is the final temperature profile. Now let us move to the second question. Our second question is based on tangential flow in an annulus with viscous heat generation. In this problem, the fluid is present between two coaxial cylinders, and the outer cylinder rotates with constant angular velocity, creating tangential flow in the fluid. This motion causes viscous dissipation, which generates heat inside the fluid. The velocity profile is first obtained from the equations of motion and then substituted into the energy equation to determine the temperature distribution. That is what we have in this problem, and that is what we are going to do in this problem. After that, we have the statement for the question. We need to determine the temperature distribution in an incompressible Newtonian fluid between two coaxial cylinders, the outer one of which is rotating at a steady angular velocity of omega naught, and these are some of the given conditions. So let us start with the solution. So the given things are incompressible Newtonian fluid, steady laminar flow, outer cylinder rotating with angular velocity omega naught, inner and outer wall temperatures T1 and T2, constant properties mu, rho, k, and cylindrical coordinates. Assumption is as follows: there is no velocity in r direction, in z direction, all the velocity is only in theta direction, and that is changing with respect to r. Dou p by dou theta is equals to 0. The equations of motion We have three components: r component, theta component, and z component as follows. As velocity in theta and z component is equal to 0, so we are getting this as 0 and 0. Then velocity distribution is given to be as these equations, and from these equations, after integrating this equation, we'll be getting this equation. Put moving r to that side, we'll be getting the value of v theta. That is the velocity distribution. Now applying the boundary conditions, from the first boundary condition, r is equals to kr, v theta is equals to 0, and r is equals to r, v theta is equals to omega naught r. So after solving it for the constants, we'll be getting in this equations, we need to put that, and then we can get the value of C1 and C2. Putting the value of C1 and C2 in this equation, we'll be getting the final velocity distribution for this question. Now the energy equation for the steady state heat transfer with viscous dissipation, we have this, and after substituting the velocity gradient this into that equation, we'll be getting this equation. Introducing the dimensionless variables, we are assuming this two dimensionless variables, and we are going to introduce that. Then after we'll get the value of n as this, and the governing equation will become this then. Solution of energy equation. So this is the solution of energy equation, and we'll be getting the value of this as this nan. After applying the boundary condition for theta, which is as follows, we are going to get the final result of this. So we get the temperature distribution as this. So the conclusion is that the temperature distribution in an annular tangential flow depends on the both radial conduction and the viscous heat generation, and the viscous dissipation है वो significantly affect करता है temperature profile को. Then we have third question, that is on heat conduction from a sphere to stagnant fluid. These problems deal with steady radial heat conduction in a spherical system. Since the fluid is stagnant and convection is absent, heat transfer occurs only by conduction. From the temperature profile, the surface heat flux and Nusselt number can also be obtained. So this is the statement for this question. We have to solve it for A, B, C, D part. In first part, we want to find the differential equation. Then we need to integrate that equation. Then we have to prove this Nusselt number is equals to 2, and then we have to find the difference between the biot and Nusselt number. So the given state the things are steady state heat conduction in the fluid surrounding a sphere, spherical geometry, and constant thermal conductivity. The boundary conditions is given as this. We need to take some assumptions like heat transfer in radial direction, steady state, no heat generation, and constant thermal conductivity. So for the differential equation, first we are going to apply the heat balance over a differential cell of thickness delta R for spherical shell. So after multiplying the surface area to the flux, we will be getting this input minus output, then dividing it by delta R and deriving it, will be getting this equation. Then using the Fourier's law, we have the flux equation is minus k dt by dr. Putting this q r over here, we will be getting this equation. Then integration and constants. After integrating, we need to integrate this equation. We will be integrating this equation to get this. Then the temperature equation after integrating this will be getting this. Applying the boundary conditions, so we have to find the C1 and C2 in order to get this temperature profile. So we have to apply the boundary conditions for that, which were given here. And after applying the boundary condition, we will be getting C1 and C2 value as this, and the temperature distribution therefore will become this after putting these two equations over there. So this is the temperature distribution. Then C part, heat flux and Nusselt number. So as we know, we have this from the heat flux from Fourier's law is this, and after putting the differential temperatures dr minus T infinity and R in place of dt by dr, we will be getting this, and this is from the Fourier's law. From the Newton's law of cooling, we have Qr is equals to H Tr minus T infinity. So this, after equating this two, we get this. H is equals to K by R, and Nusselt number is equals to Hg by K. Putting H is equals to K by R, will be getting Nusselt number is equals to 2. Now, what is the difference between the Biot number and Nusselt number? Both have the formula HL by Ks and HL by Kf. But the difference is that the Biot number uses the thermal conductivity of the solid, whereas the Nusselt number uses the thermal conductivity of fluid. So these are the final results. Now the conclusion is the temperature profile around the sphere decreases inversely with radius, and for pure conduction around a sphere in a stagnant fluid, the Nusselt number is equals to 2. Next to it, we have the last question, that is annular flow with the inner cylinder moving axially. In this problem, a cylinder rod moves axially inside a cylindrical cavity. The fluid in the annular space moves only due to the rod motion, since there is no pressure difference. And using the cell balance and Newton's law of viscosity, velocity distribution, mass flow rate and viscous force can be derived. So let us see what's this question. So this is the statement for this question, and these are the four things that we need to find, that is the velocity distribution, mass flow rate through annular region, then viscous force acting on the rod over the length L, and plane slit formula multiplied by the curvature correction. So the given things are a cylindrical rod of radius kr, which is moving axially with the velocity v0 along the axis of cylindrical cavity of radius r. These are the boundary conditions that we are given with, and these are the boundary conditions here. And then the assumptions like steady state, incompressible fluid and laminar flow. So only axial velocity exists, so there is only velocity in the z direction with the change in respect of the r, and there is no velocity in r and theta direction. dp by dz is equals to 0. So for the A part, the velocity distribution in the narrow annular region, the momentum balance is the same as that for a axial flow in the cylindrical shell, but with the pressure difference term omitted. Adding the contributions to the shell momentum balance in the z direction. So we have this in r direction, and we had added up the shell momentum balance for the z direction. So we will be getting the overall shell balance as this. Then dividing it by 2 pi L delta r and taking the limit as delta r tends to 0, we'll be getting this equation. Then simplification of momentum equation, we have phi rz is equal to tau rz plus rho vz. Phi zz is equal to p plus tau zz rho vz. Since this is what we are given with, also because the pressure at both the ends is the same and there is no imposed pressure difference driving the flow, so we are having phi zz at z is equal to 0 minus phi zz at z is equal to L divided by L is equal to 0. Hence the equation reduces to d by dr r tau rz is equals to 0. From integrating this, we will be getting this constant and C1, and from the Newton's law of viscosity, we already have this. In place of tau rz, if we will put this, then this is the equation that we get. After integrating that equation, we will be getting the viscosity distribution in terms of C1 and C2. And if we introduce this dimensionless constants in this equation, we will be getting this equation, and the constants are determined from the no slip boundary condition and the boundary conditions which we are given with. From there we can find d2 and d1. After putting d2 and d1 in this equation where we introduce the dimensionless constant, we can get the velocity distribution, which is vz is equals to v0 ln of r by r ln of k divided by ln of k. Then second part is mass flow rate through the annular region. The mass flow rate, we have to integrate the mass from 0 to 2 pi in theta direction from kappa r to r for r direction. Rho vz r we need to integrate for the mass flow rate. So substituting the velocity distribution vz ki jagah if we'll put this, then we'll be getting this equation after taking out the constants. And we are also introducing here the dimensionless constants like epsilon is equals to r by r. So we'll be getting this, and after replacing dr with this and r ki jagah we'll put this, we'll be getting the value of mass flow rate as this. Hence, the overall equation will be getting for mass flow rate is this. The third part is viscous force acting on the rod over the length L. So the force ka equation, we have this, we have to integrate for d theta dz from 0 to L, 0 to 2 pi. Velocity distribution is this, so we can differentiate it to put that in that equation. From integrating it, we will be getting the equation for force, and this is the equation for force. And the last part is free state formula multiplied by a curvature correction. For curvature correction is this, you're taking the ln of this, then for the Taylor expansion, which is as this, we can expand it, and the final f ka value force expression will be getting this. So these are the final answers. So thus for the angular flow caused by the rod motion, the velocity profile is logarithmic. The flow rate and viscous force can be obtained directly from the derived profile. For a small gap width, the result approaches the plane slit formula with curvature correction. So these are the conclusions. Thank you.